So we will begin talking about logarithms now and logarithmic functions to some limits. And I will just say that for many this is a completely abstract concept. But I will tell you that a logarithm is in short it's an exponent. So as we think about it, think about our exponential functions and what they look like. If we were to take our exponential function and go ahead and, we have y equals x squared, and this is that exponential function that they're graphing right there. If you were to turn around and find its inverse, where x equals 2 to the y, of course you would reverse all your xy coordinates, and then you would have this graph right here, and this would be x equals 2 to the y exponent. And what this is, it turns out that this is a logarithmic function. This is my exponential function, and I hope that you can see when we look at that, those are actually, you can see that it's the inverse function, because it is mirror imaged over this y equals x. So that's one of those characteristics of an inverse, is that it is a mirror image of itself there. So just something to consider, that as we think about logarithmic functions, they're really nothing more than exponents. We do want to be able to rewrite the expressions in exponential form and then go from exponential form to logarithmic form, and that's really just understanding the form, fit, and function and the shifting of it, and then again graphing to a limited bit. Understanding that here they're saying, hey, the inverse right here, the inverse of y equals 2 to the x power can be defined as x equals 2 to the y power. So looking at it as we do this, it's going to turn out to be that the natural log of x is b to the y power. So y is called the logarithm, base b and x. So here, being able to write it as y equals the log of base b to the x, or of x. So, and it reads log base b of x, this being the base. And that's really important if you think about it, because when we talk about an exponent, if this is my base in the logarithm, that is also my base when it comes to the exponential function. So those two things are going to be the same. So here, as we look at this concept, base b, if you see a logarithm base 2 of 8 equals y, then they're saying that, again, 2 is my base, the exponent is y. Remember I said your logarithm is equal to, your exponent, and then equals 8. And then we quickly learn what does that mean, and we're going to go through and do some, just like when we did exponential functions just a little bit ago, or equations, exponential equations. When we had the base, we had like bases, we could make the exponents equal to each other, therefore y is equal to 3. So again, like bases, this would be exponent y, this would be exponent of 3, and then again they're saying, hey, what exponent do you multiply 2 by to get to 8? So that y value is just my exponent. So that's a jump into the exponents, but being able to reorder them, and I know some students will jump right to putting these into the calculator, and in some respects they can do that, but you may not be able to do it all the time, or should I say just doing it is faster than trying to put it into the calculator. So being able to read this, log base 4 of 64 equals 3, and what they're trying to say, what exponent do we raise 4 to get to 63? So again, 64, we are reordering that and understanding what they're saying, and if we put that into the calculator, it will give us 3. But we are saying that when we take 4 raised to the third power, it equals 64. Okay, there's my base, there's my exponent, and there's my answer. Again, now this one's a little bit trickier. When we think of this, you have to think about 1 over a number is going to be a negative exponent. Okay, so remember that if this is to the negative first power, if I wanted to take this, or sorry, to describe that, If I wanted to take that and bring it up top, it would be 247, no, it would be 243 to the negative 1 power. So that's why we have to think about what's going on there. How did they come up with that negative? That's how they came up with that negative. So keeping that in mind, that this 3 raised to some exponent three raised to some exponent is going to be 1 over 243. So again, we have 143 is 1 over 4 to the 5th, which would be the same thing as 4 to the negative 5th. So that's why they're saying, hey, 4, it seems like that must be, had to go through and fix my typo. That is 3 to the negative 5th, so 3 to the negative 5th is actually the same thing as 1 over 243. Again, 9 raised to some exponent is going to be 3. You know, the 1/2 exponent is the same thing as the square root of 9. So again, using these same skills. Being able to rewrite this log, we have a base of 125, so we know that 125 raised to the 3rd exponent is going to be equal to 5. And that's what they're asking us. And thinking about that too, that is the cube root to 125 is equal to 5. So just being able to reorder this using the math skills that we've already learned. Again, here going from exponential to logarithmic form, again, being able to identify this is my base and this is the exponent, so that is what we're equal to. So, you know, the log of base 7 is equal, 7 raised to some power is equal to that number. So 7 raised to some power is equal to that number. So log base 7 of 117,694 equals 6. So that's how we're reordering that, understanding that. Let's see, and I know a lot of these will go into the calculator, except for, you know, you need to be able to reorder them. Okay, so again, the log of base 8 of 4 is equal to the exponent of 2/3. So being able to do that. So here I have the log, and my base is going to be 2. Log of base 2 of 512 is equal to 9. So 2 raised to the 9th power is 512. So just being able to work with that. Evaluating this logarithm, it's going to be the same thing, oftentimes with these exponential functions, where we were making sure that we had like bases. So the being able to reorder at this point is saying that 216 raised to the y power is equal to 6, and then we work to get our like bases. Again, power raised to a power is going to be 3y, so we know that 3y is equal to 1, or y is equal to 1/3. Can you put that into the calculator? Yes, probably can. But we need to we need to understand the way that we manipulate back and forth from exponential to logarithmic, from logarithmic to exponential. We need to understand that process. So the calculator can give an answer, but it doesn't help us understand the process. Okay, here's air pressure, and we have some number raised to an exponent, right? Air pressure outside an aircraft can be determined by the equation. Probably pressure is equal to B times 10 raised to the negative 9h over 100, where B is the air pressure at sea level and H is the altitude in miles. If the air pressure at sea level is 14.7 pounds per square inch, write an equation to the height of the aircraft when the pressure is known. So B being my air pressure, 14.7, looks like they're cross multiplying or simplifying. P divided by 14.7 is equal to this. And I guess, what have we done here? log base 10 of both sides by taking the log base 10 that is a property, and so they took log base 10 of both sides. So when we take this, and just thinking about it, we have the log of base 10 of 10 raised to negative 9h over 100. And I think what they're saying is well, this number raised to what exponent equals this? Well, this number is this number, so I just need to raise it to this exponent. So it's sort of an identity, a definition, that if I have base 10 and 10, I know that that simplifies to that exponent because, again, the log is the exponent. So that's what happened to my 10 over here. And then if they raised one side to the log of 10, they have to raise the other side to the log of 10. So that's where that came from. Isolating h, well, you would have had to multiply by the reciprocal 100 over negative 9 on both sides to get h. And ultimately, you can now solve. And then the distance in miles from a tornado travels this, where W represents the speed of the wind per miles. Write an equation to find the wind speed when the distance traveled is known. So here, it said write an equation to find the wind speed. So we have the W is equal to 10 raised to some power, so we need to take the log of 10 of both sides. Log 10 of y of one side is equal to the log 10 of 10 raised to this exponent. So again, that equals my exponent. So 90, and then I multiply both sides by 93. So that will simplify. 93 times the log base 10 of y, and then now I'm going to go ahead and add 65 to both sides. So now I have W by itself. W is equal to 93 log base 10 of y plus 65 equals W. And then it says what happens. Use the equation to estimate the speed of the winds to the nearest mile per hour if a tornado that travels 50 miles. Okay, let's see if we plug that in. Because distance, right? Distance is W, or is Y. So we can plug this in. So we're going to put this in the calculator. And ultimately, I'll plug that in the calculator and see what the value is going to be. So here, when I put it into the calculator, of course, to get to the log base, if you need to, you can use your math button, and you have log base, which allowed me to type it in here. So I went just 93 times the log base 10 of 50 plus 65, gave me an answer. Now, what we learned, though, is a logarithm, if you don't see a logarithm base, then we understand it to be 10. So you can actually just use the log button on your calculator for base 10. So you can see here where the log button is at. It is right here. Here's your log button, and in the future we'll be talking about the natural log button. So understanding that, being able to look at a logarithm, we are going to do very limited graphing of these functions, but I would hope that if you look at it, you can apply the characteristics that we do understand. You should be able to look at it and see its domain and range. Seeing that we have an asymptote is going to be the y-axis versus the x-axis, which was the asymptote for exponential functions. You should be able to look at this and be able to identify that what is my x-intercepts, what is my in-behavior. Those kind of things you should be able to recognize just based on your understanding of those words. And as we look at the shifting and transformations of the function, we can see the same characteristics that we've used for all of ours, where we have x minus h inside the parentheses, which will move it left and right. You have the a on the outside, which will stretch it or shrink it or flip it. And then you have the k on the outside, which will move it up and down on my y-intercept. So these characteristics are very enduring. So then just being able to look at these and understand what is going on with my in behavior, we can see here my asymptote appears to be the y-axis, or x equals 0. We have a y-intercept an x-intercept at 1, 0. My domain, let's see here. My domain is going to be all positive real numbers because it never touches 0, so we never have negative numbers. So looking at that in behavior, this is a little bit different. As x approaches 0 from the positive side, y is going to negative infinity. And then as x approaches positive infinity this direction, y is approaching positive infinity. So there you go. Just being able to, articulate that based on our definitions that we've learned in the past. Again, here, not going to worry too much about this, but just again, being able to, this is a rehash of what we are just talking about. Not going to be graphing, again, not going to graph these transformations. So that is beyond the scope of what we want to learn right now. But we do want to continue on with the properties of logarithms. And the property of equality of a logarithm. Let's see, if b is a positive number other than 1, then log base b of x is equal to log base b of y if and only if x and y are equal. Okay, so what they're saying is if everything else, like our exponential functions in the past, if everything else is equal, then those two remaining items are going to have to be equal too. So when I look at this, the log base 3 of x is equal to the log base 3 of 7. Well, it would behoove me to understand then that 7 must be x. So that's what they're telling you there. So we can start creating these equations based on what we see on the inside. So here, let's see, solving logarithmic equations using the properties of equality and simplifying and evaluating expressions using these. All right, so the log base 4 of x is equal to 5/2. So what they're saying is 4 raised to 5/2 is equal to x. That is what they tell us. Now, you can put this into the calculator and go there, but you have to be able to understand this reordering to get to the calculator to be able to plug that in. Do you need a calculator for this? Absolutely not. But this is just remembering what a fractional exponent is. Being able to raise these to the powers, this would be 2 raised to the 10 over 2 or 2 to the 5th, which is 32. So just being able to make this manipulation to where you can continue on. So here's a good example where they said if the log base 5 of 2x squared minus 6 is equal to the log base 5 of 4x, we know then that since this is the same, so too is that. Okay, so that's what they did. They eliminated log base 5 on both sides because they know that those innards should be equal to each other. And then so we go ahead, this is a quadratic equation, so we want to get it in the standard form so we can factor it. Never going away, that factoring thing. So subtracting 4x from both sides, 2x squared minus 4x minus 3, all divisible by 2. So just divide everything by 2 real quick. So it'll be nice and easy because then we end up with just x squared minus 2x minus 3. And if you forgot, over here when I divided 0 by 2, I still have 0. Okay, factoring that, we have x minus 3, x plus 1. Making both those factors equal to 0 tells us that x is either 3 or negative 1. Okay, so again, using those properties of equalities. Coming back here and checking it. If x is 3 and x is negative 1, well, we can actually never find a logarithm of a negative number. Remember that it went from 0 and got greater in the positive direction. There were no negative numbers. So therefore, we could not find the log of a negative number. So this one is my only solution. So there's that extraneous solution that we would have come up with. Came up with an answer that technically was not a true statement. Okay, here's, let's do this. Take a moment, stop the video, do this. All right, so if the logarithm and the base are the same, then we know what's inside here should also be equal. So log base 13 of this is equal to the log base 13 of this. Therefore, negative 5x is equal to negative 2x squared plus 3. There we go. That's where we start. Now we have to have. I want to have that the x squared. I want to have that positive. It's just going to make things easier for me. So I go ahead and add 2x and subtract 3 from both sides. So I have everything on this side of the equation now. Now factoring, x does not equal 1, or the coefficient is not 1, but I do know that the only factors of 2 are going to be 2 and 1. And then I just have to figure out, well, I have only one set of factors for -3, and that is going to be 3 and 1. And which one will end up giving me -5? Well, if I take my -3 here and I take my +1 here, when I go and do the FOIL method, if I were to check it, this would be 2x squared, this would be -6x, and this would be 1x. So -6 plus 1 is the answer I was looking for. So again, 2x plus 1 is equal to 0. X minus 3 is equal to 0. So x is going to be equal to 3. And over here we end up with subtracting 1. We end up with 2x is equal to -1. Well, that's not going to work out for us because x, well, let's see, can x be -1/2? Well, let's see. -1/2, let's fill it in. -5 times -1/2 would be okay because that would just give me a +5/2. Over here I'd have -2 times -1/2 squared plus 3, and that's going to be equal to, that should be equal to -2 times 1/4 is plus 3 is equal to, it's going to be a positive number, right? Let me see here. This comes out to be -1/2 plus 3, or a 2.5. 3/2. I'm sorry. Yeah, 2.5. 2.5, right? So yeah, so our answers here should be, well, turns out they're both 2.5. Look at that. All right, so the properties of logarithms. The product of the sum, let's see here. Think about this, and I know this video is going to get a little bit long, but that's fine. We're covering 2 sections. But remember, when we have like bases, right, we add the exponents. If I take x to the first times x to the first, that is x to the second, because like bases, we add the exponents. Well, if you look, when I have a base, 2 things being multiplied together, that is the same thing as adding them separately. Okay, so it's very similar as the exponent rules. So I can separate this into its factors and add those things together independently. All right, so that's what they're saying. So this could be the same thing as the log base 5 of 8 plus the log base 5 of 4. So being able to reorder that. Division, you got to remember when we are dividing like bases in exponents, we subtract them. So therefore we have this subtraction rule. And then a power raised to a power. When we have a power raised to a power, we multiply them. And that's basically what we have here. We have a power raised to a power, so we are multiplying that power value to it. So just being able to reorder these things, and of course, I guess too, knowing that log base 10 of 10 is simply equal to 1, because again, 10 to what exponent is equal to 10? Well, that answer is 1. Okay, so that's just one of those, definitions and identities that helps us work. So here's a couple of examples. They went ahead and worked through, this is going to be, they've given us an approximation. So what we've done is they said, hey, if you can get this narrowed down to log base 3 of 5, we're telling you this is the decimal for it. Here is log base 3 of 405. So if we can get it down to factors of 5, then we can simplify. So this would be the same thing as 5, right? 5 times 3 to the 4th power. And in doing so, remembering this is the same thing as bringing the 4 out right there. So it would end up being 4 times 1. Or 4, and then this would be log base 3 of 5, and they gave us that decimal place already. So they just substituted that in and they came up with a final answer. So that's how we're working with these. I guess take a moment and do this one and then check your answer. Okay, so I went ahead and did a lot of steps over here so you could just see what's going on. The log base 8 of 320 is also equal to 64 times 5. I knew it was going to be divisible of 5 by 5 because they gave me that as part of my, question. Then I know that that would be the log base 8 of 64 plus the log base 8 of 5 because I'm using that addition property. Here, then I know that 64 is technically 8 raised to the second power plus the log base 8 of 5. And I could have converted this to a decimal at any point in time. I just waited until the end. Knowing the power rule, this 2 is actually going to be moved out front, so I have 2 times the log base 8 of 8. Log base 8 of 8 is that property, that identity. We know that that is just equal to 1, so 2 times 1 plus the log base 8 of 5. 2 plus 1.465 is equal to 3.465. So there's using the multiplication rule. If we go to use the quotient rule, we have the same thing going on here. This is going to be the same thing as 3 squared divided by 5. They told us that 5 is going to be this decimal, so since it's quotient, we know that log base 3 of 3 squared is going to be subtracting, right? So division minus log 3 to the 5th. They gave us that decimal, and then again we knew that this 2 would go out front, and then it would just be 2 times 1, or 2 minus that is going to give me this answer. So that is understanding that. Again, looking at your problem here, trying to work it out first, and then just think about this. Since we have this large number in the denominator, it's going to be a negative exponent because that's what would have put it. It'll be a positive exponent in the denominator, but when we move it up into the numerator, I guess we don't have to. Never mind. Disregard. So go ahead and work with that. We'll see what values, but look at the base. The base is 6. There's a good chance that this number is a something 6 to the some power. So there you go. The log base 6 of 5 minus the log base 6 of 1296. So I went ahead and did this as a decimal, and I just carried on down. So that would be minus the log base 6 of 6 raised to the 4th power. Again, the power rule, that becomes moved out front. This becomes a 1. So 0.8982 minus 4 is going to be negative 3.1018. Now, I said that you cannot find the log of a number. I didn't say that the result could not be a negative number. I'm sorry, you couldn't find the log of a negative number. I did not say that the result could not be a negative number. So just keep that in mind. And then here, the power property. Again, something raised to the number is the same thing as multiplying it by 4. So there you go. The log of base 2 of 1296 is actually, like we said, 6 to the 4th power. Move that 4 out, so we have 4 times the log base 2 of 6, which is approximately 2.585. Multiplying that out, you end up with 10.34. And then, let's see, this one should be, let's see here, we have the log of 2, and then, this could be multiples, huh? So go ahead and give it a go. Okay, so looking at this, it says use log base 2 of 3 is approximately 1.5850. Then the value, approximate the value of this. Well, you got to remember that 243 is actually going to be the log of 2, base 2 to the 3 to the 5th power. Reordering that, that's going to be 5 times the log of base 2 of 3. They told us the log, never mind. They told us the log base 2 of 3 is that, so that would be the same thing as 5 times 1.5850, and that would give us some value of approximately 7.925. 7.925. So that would be the approximate answer there. Now, again, practice and just being able to work on these and manipulate these functions back and forth between logarithmic and exponential form. Not difficult, it's just remembering the form, fit, and function. It takes practice reordering these things, and we'll work on this problem in class. So again, we're going to get some